Hello and welcome. Let's look at lesson 3-4, differentiating inverse trigonometric functions. I know it has that crazy word inverse. Don't let that throw you because today much easier than lesson 3-3, which was just inverse functions. Today we're on inverse trig functions. So to complete our study of the derivatives of trig functions, we got to look at the inverse of those 6 trig functions, and that's what we're tackling today. Um, a quote from the AP exam. These AP exams always start out with this in their introductory part. It says notation. The inverse of a trigonometric function x may be indicated using the inverse function notation f raised to the -1 or with the prefix arc. Example, sine -1x, which is equal to arc sine of x. So just know that be flexible in your work, that you can see that either way and interpret it. The inverse trig derivatives, these are things, the final 6 things we have to memorize. So it's going to be written in chain rule style because we're going to use u as our function. So sine inverse, it will be a u prime over square root 1 minus u squared for the derivative of sine inverse of u. Secant inverse is u prime over absolute value of u square root u squared minus 1. And tangent, well, it's got that chain rule idea, so we got a u prime there, and it's 1 plus u squared. So a little bit easier there, 1 plus u squared, no square root. Oh, there's 3 more to memorize. Have no fear, though. These are easier. Notice derivative of things starting with a c. Like the first 6 trig functions, if they started with a c, it was a negative. That is true on these as well. So derivative of cosine inverse is identical to sine except for the additional multiplication by a negative. So we get 1 minus u squared. Cosecant will follow secant, except it is negative. So I get negative u prime, absolute value of u square root u squared minus 1. And cotangent will be a negative u prime over 1 plus u squared. In my head, I was thinking I wanted to tell you that I would say this one here and this one here tend to be the main focus of the AP exam. Okay, well, let's do a few. These are going to be fairly fun today. The derivative of sine inverse of 3x. Well, 3x is my u part, right? This is what I'm looking at right there. What is inside the arc sine? My u equals 3x. That means u prime is equal to 3, and u squared would be 3x squared, all in parentheses, so that's a 9x squared. Sometimes I like to lay out those components I'm going to need because I know I need a u prime and I know I need a u squared. So maybe I just want to build myself an informational box over on the left side, and now I'm going to go in and do this derivative. So I don't know why Word is starting up, but whatever. All right, u prime, 3 over square root 1 minus u squared gives me 3 over square root 1 minus 9x squared. Oh, the 1 didn't show up. There we go. 1 minus. Tangent inverse. Here's my u. U is equal to 2x squared. That means its derivative is 4x, and its squaring would be 2x squared getting squared. So that's going to be a 4x to the fourth. 4x to the fourth. Now I go and find the tan inverse formula for its derivative. This derivative would be equal to a u prime, and I know u prime was 4x, over, no radical when we're working with tan inverse, 1 plus u squared, 1 plus the u squared. I'm showing it. I could have just written it straight down, but I wanted you to remember where this stuff was coming from. 1 plus 4x to the fourth. Arc secant. Well, arc secant's going to have this recipe to it, and we just got to fill it in, don't we? Okay, that 4 way out. Looks like arc secant raised to the fourth. So it's a little bit more definitely inside. We're going to be taking the derivative of the arc secant of 5x. But I also have this power of 4. So composite function with like 3 levels to it. And this is going to be a chain rule application. So we've got a chain rule of arc secant, right? Is really what's going on this one. So outer function, I'm going to erase so I have a little bit more space. Outer function is the 4. So this derivative, I'll just say y prime equals 4 comes down, changes to a third power. The inside piece, which I've got like f of g of h, the g of h stays the same, and this would be like my inner two functions. So I'd have arc secant of 5x remaining inside. Now I've got to chain off and take the derivative of arc secant. I'm going to write that down. Arc secant of 5x. We need its derivative, right? Just to slow this process down a little bit. Y prime equals 4 arc secant of 5x times, now let's get the derivative of arc secant. That's the one that goes u prime, which would be 5, over absolute value of u, 5x, times the square root of 5x squared minus 1. Could clean up a little bit. Beginning stuff looks just fine. Let's just recopy that. But this 5 really could come outside because I can bring it out as a positive 5, which it was anyway, and I can get those 5s to cancel. And then I can have this over absolute value of x, still need the absolute value on that, and square root, let's expand our 5x quantity squared to a 25x squared minus 1. I like it. That works. Problem 4. Cosine inverse of e to the 2x. There is our u, isn't it? Do you remember how to take the derivative of e to the u? The derivative of e to the u is e to the u times u prime. Okay. So, laying out the derivative, I'm just going to say y prime equals. I would have e to the 2x, I need to get its derivative over square root 1 minus the u part squared. And since it's cosine, it's a negative, isn't it? Now, let's keep working. This one's got a little bit of stuff to it. The derivative on top, well, derivative of e is e to the u times u prime times a 2 is a derivative of 2x over the bottom of square root 1 minus, if I square e to the 2x, I get power raised to power. Then I multiply them. I get e to the 4x, not 4x squared. It's basically done. The only thing I'm going to do is get that 2 in front, and I will feel so much better. Okay, there we go. Tan inverse of square root x is our next problem. So our u is that, which really is square root x, or I could think of it as x, not u, x to the 1/2 power. But many of us have it memorized that it's 1 over 2 square root. That makes it fast. And then a u squared is going to be just x, isn't it? Square root x squared will give us just x. The pattern for the derivative, so dy dx, is equal to u prime, which is 1 over 2 square root x, divided by 1 plus u squared, which is just x. Now, everything is almost perfect, except that I've got a complex fraction, don't I? So I'm going to multiply by the reciprocal of that denominator. dy dx equals 1 over 2 square root x times 1 over 1 plus x gets me dy dx equals 1 over 2 root x, parenthesis necessary, 1 plus x, quantity. Very nice. Number 6, find the equation of the tangent line. And we got arctan at the point where x is a square root 3 over 3. Arctan, u prime over 1 plus u squared, right? That's our derivative pattern. So why do I have these little dashes and then I can't move it? Okay. Some pen ink. Y prime. If I'm making the equation of a tangent line, I definitely need the derivative. So the derivative, u prime, that's going to give me a 6x over a 1 plus 9x to the fourth, right? And that's going to yield that. And we want to evaluate at root 3 over 3. So y prime evaluated at root 3 over 3 would be 6 times root 3 over 3. Oh, that's going to reduce. Over 1 plus 9 root 3 over 3 raised to the fourth. Oh, wow. Okay, one little bit at a time. 3 goes into 6 2 times, so my numerator is set. Like in that. 1 plus 9 root 3 is like a 3 to the 1/2, and it's going to get raised to the fourth. And then this 3 on the bottom gets raised to the fourth. I'm just going to take it really slow so I don't make a mistake. 3 times 4 gives me 2, doesn't it? So I've got 2 root 3 over 1 plus 9 could be written as a 3 squared. And then 3 to the 1/2 raised to the fourth is multiplying those exponents. That's a 3 squared over 3 to the fourth. Oh, that's a 3 to the fourth over 3 to the fourth, which makes 1. So I've got a 2 root 3 over 1 plus 1. Oh, 1 there. Gets me a 2 root 3 over 2. Would you believe this comes out to be just a root 3 for its derivative? Now, we are not quite done. That was derivative work. So in order to write the equation of the tangent line, we also need the point, and they did not give us the y value. So we've got a root 3 over 3, comma, y. To find y, we go back to the arctan equation of 3x squared. What does arctan mean? Well, if I took tangent of both sides, I would get tangent of y equals the tan of the arctan, which zaps each other, equals a 3x squared. If I plug in the root 3 over 3 quantity squared, I'm going to get 3 over 3 squared. So I'd have 3 times 3 over 3. I'd have a 3 times a 3 over a 3 squared, which is going to turn out to be simply 1. So now I'm down to tan of y equals 1. Where does the tangent of something equal 1? You could also, I'm kind of taking it back where we started, but that's okay. Well, that is at pi over 4. So my angle is pi over 4. My y value is pi over 4. We have the point root 3 over 3, pi over 4. This stuff was all pre-calc stuff. Let's write our equation. Y minus pi over 4 equals the slope. Our slope was over here, root 3. X minus root 3 over 3. That was quite an involved problem. Here we pick up a few like AP type problems. So let's walk through those. Let g of x equal arc cosine x squared raised to the 5th. 2-level, well really 3-level problem, but an outer function of 5. So we're going to take its derivative. G prime of x. Derivative of the outer function first. 5 comes down by power rule and reduces by a power, making it a 4. And then we got arc cosine of x squared. Then I've got to chain off and take the derivative of cosine inverse of x squared. That's a u prime. So u prime. This is my u, isn't it? So I'm going to have a 2x over square root 1 minus u squared, which would be an x to the 4th. All right. G prime of x. You might be able to find the answer already. They used arc. Okay, so I'll use arc cosine of x squared multiplied by a negative. So I'll bring my negative out front. 5 times 2 gives me negative 10. X, bring all of that out front, over square root 1 minus x to the 4th. By now you've seen enough answers that you kind of know how people like to simplify and write them down. Did we hit something good? Negative 10x, x arc cosine x squared to the 4th. Oh, the x squared doesn't work in my book. This is the x to the 4th that we need, but it's not negative, so it's not this, it's not this. Negative 10x cosine squared to the 4th, 1. I think we're right there. This didn't have an x. This didn't have a negative. Okay, I'm loving B. Number 8, limit as h goes to 0. Woo, woo, woo. Does that ring a bell? What does this setting us up to do? Well, hopefully you recognize as h goes to 0 and we've got h, this is the definition of a derivative. So this really equals f prime of x equals the limit. So all I need to do is equals 3. Which of the following could be the value of a? And where is a? A is there. So this is a derivative evaluated at a that we're trying to find. Okay, that's my overall goal. So in order to do that, I need to figure out what was the original function, just in general terms, x. And I know that this is f evaluated at x plus, actually a plus h, isn't it? Minus f of a. Well, here is my function then, arc cosine, or right there. So our original function is an arc cosine of x. And I can take the derivative of x. I know the derivative rules. Derivative of x is 1 over, well, it's negative 1 because it's arc cosine, square root 1 minus x squared. Now to finish this, I'm going to have f prime of a. F prime of a turns out to be negative 1 over square root 1 minus a squared. All of that is supposed to equal 3. So let's let this equal. So they wanted f prime of a equal to 3. So we're going to take our f prime of a, which is negative 1 over square root 1 minus a squared, set it equal to 3. Let's multiply up by that. So that gives me negative 1 equals 3 square root 1 minus a squared. Let's divide by 3 because I'm trying to solve for a. Square both sides to get rid of the square root. Got it? That's going to give me a positive 1/9 equals 1 minus a squared. Subtracting 1 is like subtracting 9/9. That's going to give me a negative 8/9 equals negative a squared. Positive equals positive, so a equals, kind of thinking plus and minus, square root 8 over 9. Now that may be an answer, or maybe they reduced things. They did, I can see they've got a 3 denominator. If I take the square root of 9, I can do that independent of the numerator. So I'm getting square root 8 over 3. Fabulous. Square root 8 over 3. I'm getting A. Hope you did too. Whew. Number 9. I'm getting exhausted, you guys. Number 9. Arctan of y equals natural log of x. And they want the derivative of y. Ooh, implicit differentiation, because I cannot separate my y, can I? So this is going to be an application of implicit. Do you see how you have to keep your mind very flexible and think of all the things that we've learned up to this point? They come into play when you least expect it. I recognize implicit differentiation because I have a mix-up of x and y's. So arctan of y, my y is my u. U prime over 1 plus u squared. Squared, not prime. Natural log, do you know its derivative? 1 over x, right? All right, so we can take the derivative of both sides. What I'm going to write down is that we're going to take the derivative of each side in order to get dy dx. So the derivative of arctan of y would be the derivative of y over 1 plus, sorry, I've got a tickle in my throat, y squared. That equals 1 over x. I want to solve for dy dx or y prime, different way of writing it. So I get y prime equals 1 over x multiplied up by 1 plus y squared. That's like it's over 1. And I get y prime equals 1 plus y squared over 1. Oh, I'm sorry, over x. 1 times x. Any of these look good? I'm like an E. One last one. Number 10. Another derivative one. This is equal to, you better know this one. This is equal to f prime of x, isn't it? What is your f of x? These are going to keep flying at us all year long till you really can just do it so easily. Okay, if my function is sine, then the derivative of sine, you know it, you love it, is cosine of x. And it's not evaluated at any place because I see the general x in there. All right, this last page is really just a review of pre-calc to bring that back in your memory. The first part talks about the domain of an inverse function. Remember, in order to get an inverse function, so we know our function sine looks like this. In order to have an inverse, we have to restrict our domain because an inverse function not only has to pass the vertical line test, it has to pass a horizontal line test. And the only way that's going to be able to happen is to restrict our domain over some region. And the region selected for tan is not 0 to 2 pi, is it? If you recall in pre-calc, it is, let me see here. It is negative pi over 2 to positive pi over 2 right there. So we really just get this band of y values, which really covers everything from -1 up to +1. So we have all our y values covered. And so sine x has, if you've got a highlighter, highlight that region. That is its restricted domain. So the restricted domain is -1 to 1, but the range would be negative pi over 2 to pi over 2. Cosine is restricted to right here. We go 0 to pi on it. That will cover all the values from 1 to -1, because that's what the values of 0. Cosine of 0 is 1. Cosine of pi is -1. And so we capture all those domain values, and it's over this restricted range. And finally, tangent, it too is like sine. It goes, whoopsie, we're drawing something funky. It goes from there to there. So highlight that. So tan, inverse sine have the same restricted values. Cosine's the one that's different. So it says f of x is equal to arc sine at x equals root 3 over 2. Evaluate the function at the given x value. So this would look like an, oh, that's not going to write well. Let's look at f of root 3 over 2 equals arc sine of root 3 over 2. So on the unit circle, whose value comes out at root 3 over 2? For sine, I know that I have to stay within those values, right? So whose value is that? Because in my head, I'm thinking sine of some y value turns out to be root 3 over 2. Root 3 over 2 happens right up there, right? The ordered pair is 1/2 root 3 over 2. And so I'm looking up for the answer to give me the input, and the input value then was 1/2. So f of root 3 over 2 ends up being 1/2. The answer to an inverse arc sine of root 3 over 2. Cosine inverse of x over 4. So I'm evaluating at -2 here, it looks like. And I'm going to pop in then -2 where I see x. That would be like saying cosine inverse of 1/2. So this is kind of a backwards wording, right? So I'm looking for the cosine of some value equals 1/2 if I want to interpret it as a cosine instead of a cosine inverse. For cosine, where do we need to restrict ourselves? Right along here. So are there, or is there one spot where the output value is 1/2? Yes, there is, right here. 1/2 comma root 3 over 2, the one we just finished using, connects with the angle value of pi over 3. So y equals pi over 3. Just getting you familiar with how to look up those values. And you know what? I am tired. I'm going to call it good on that. You can do number 12 on your own if you wish. Your homework is going to be a Delta Math assignment, so log in and work on those.